Okay, so lab exercise 6. 555 timer circuit and soldering. So the objectives of this lab exercise are for students to understand the 555 timer, which is an integrated circuit we'll talk about a little bit. 2, to be introduced to digital circuits. 3, to learn to solder. And 4, to analyze and build relatively complex circuits. So, materials. The following materials are required for each lab station. Well, that's too close. So the usual things, a few things that we haven't used yet, the prototyping board. So we're going to be using that. And a 555 timer integrated circuit. That's a new thing we're going to have. So it looks like a little computer chip, because it is. Great. Some resistors, an LED. That's a new thing too. We haven't used an LED yet. So fun stuff in this lab. Okay, so 555 timers. The 555 timer is a ubiquitous integrated circuit that can be used to output periodic signals loaded up to around 200 milliamps. The Pinout diagram is shown in figure 6.1. Here it is. Note the dot right here, which can be used to orient the circuit. So when you look at it, try to find that dot. It'll tell you which pins are 1 through 4 and 5 through 8. Great. So a functional block diagram is shown in figure 6.2. So that's on the next page right here. Boom. Okay, so this is what we're going to use to help understand the operation of the 555 circuit. So, good. The VCC pin 8, so that's this guy right here, VCC. 8 has its voltage divided by 3 5K resistors in green before being grounded by pin 1. So VCC is pin 8. It goes across 3 5K resistors, so 5K, 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 to pin 1, which is ground. So to pin 1 right here. Okay, so that's the input to this circuit, and these are highlighted in green here. Sometimes I guess people, I don't know. I guess apparently this is not why it's called a 555 timer, but it's quite a coincidence that they have 5K, 5K, 5K resistors. Seems kind of sketchy to me that it's not, but supposedly, according to Wikipedia, which I trust with my life, it is not the reason. So, we've got this VCC into the circuit. It's divided into thirds, essentially, right? So, the probe that comes off in between these lower two 5 kilo ohm resistors gets 1/3 of the voltage, 1/3 of VCC. Then this lead that comes off gets about 2/3. Well, as close as those 5Ks are to being exact, it gets 2/3 of VCC. So then we've got these other things that are happening here, and recognize that this is a functional block diagram. So these are actually instantiated with several components, but we're able to simplify the characteristics of the circuit with these approximations. Niles. Okay, so good. So pin 2, which is the trig pin, and pin 6, the threshold pin, pin 6, are compared by comparators to the 1/3 and 2/3 of VCC. So that's what these guys are, the yellow and the, I want to say, peach colors are. So these are called comparators. And comparators are digital electronic devices that output Boolean true when the upper terminal, sometimes called the plus terminal, when the upper terminal has voltage greater than that of the lower terminal. So the lower terminal would be this guy. So when the plus one is greater than the minus one, it outputs Boolean true. Now we haven't done a lot of digital electronics, virtually none. I mean, you've seen a little bit of it here and there, but primarily it's been analog signals in the 345 class and in this lab. It's a whole topic, and I would love to get into detail on it, but we're just getting a little bit of an introduction here. What digital circuits deal with are just two levels of voltage, okay? Low and high. So low represents false, Boolean false, and high represents Boolean true. So you can do logic with them. Instead of having a real number representing a voltage, you have to have just some high value, some low value, and they try to operate, these digital circuit blocks try to operate based on true, false in the signal. So true, false depends on there are a bunch of different conventions for digital signals. We're not going to get into detail on that right now, but suffice it to say that there's a voltage that's higher, so like maybe 5 volts, that represents true, and 0 volts that represents false. And if you're close to the lower one, it gets represented as false. If it's closer to the higher one, you represent it as true. There is this middle ground, and there's some ambiguity there, but details we're not going to get into right now. So what's happening are the trigs, so channels 2 and 6 are being compared to the 1/3 of VCC and then the 2/3 of VCC. Okay? If they're greater, so like for instance, if the threshold is greater than 2/3 VCC, then it outputs true or high here. If the threshold is lower than 2/3 VCC, then it outputs false or 0. So sometimes you would see it as 0 or 1 for false and true. And these get fed to the same device here, which is called a flip-flop. So, like a politician. I'm not sure what I thought of that joke. Anyways, okay, so great. Their outputs, so these comparator outputs, connect to an SR flip-flop in purple, which gets set to true by terminal S and reset to false by R. So this flip-flop is probably the most complicated block in our circuit here, and what it does is a little bit subtle. So when S is true, it switches on its output. When S is false, S can turn off then, it'll continue to be true at the output until the reset R is true, okay? And then the reset will reset it to false, and then S has to be true again before it'll be true on the output. And then there's this external reset R1. So this can be described as having memory. So once S sets it, even if S goes false, it will remain true. So the output of the flip-flop will remain true. Only if R, the reset terminal, goes true, will the flip-flop return to false. The reset pin 4 can reset the flip-flop state at any time. So this reset pin 4, so on your pinout, it's right here, you can use that to reset your state at any time. And so it overrides whatever the current state is. And we're going to use that. You can use it as a sort of fail-safe. And that's what we'll use it as. So if there's no input from the source, then it'll essentially just null the output. Okay. Great. Okay. If the flip-flop is set to true, two things happen. Okay, so the flip-flop is set to true by S being true. So once S is true, then the output of the flip-flop is true. First, the output is inverted. So this like circle symbol that shows up all over this diagram means inversion. So that means that if it comes out true, it immediately gets flipped to false. Okay, and then it comes down here. It also gets flipped back to true here. So it gets flipped twice, meaning whatever comes out of the flip-flop actually goes into this, but the opposite of that comes down here. So yeah. So the symbol circle means inversion. So first, the output is inverted, and it shuts off the gate for a transistor in blue, to which we will return in a moment. So notice that if this goes true, it immediately gets flipped to false, and then this transistor, which this is actually I think best represented as a BJT transistor. We haven't talked about those, but they operate a little bit like a MOSFET. So a MOSFET is a type of transistor. BJTs are transistors too. And we can think of them as having the same sort of properties. So this is the gate, right? And so current will flow through it once the gate voltage reaches a certain threshold. So they operate in a similar way to MOSFETs. So what happens is that when this flip-flop goes high, it turns the gate low. So the gate goes low and it shuts off this transistor. So nothing's going to flow from 7 to 1 when the flip-flop is high. And we'll return to what this thing does in a moment. So if this is high, then so it goes high to low to high again because it gets inverted twice. And it goes back to high. And this stage here is what happens to the output signal. So the flip-flop output is inverted again and switches on an output stage in pink, supplying power to the out pin 3. So power comes out of 3 now. And so this is the main sort of output of the 555 timer, and that comes out of 3, pin 3. Okay? Good. By the way, when you build your circuit, all integrated circuits like this fit nicely across the bridge in the middle, the spine or bridge of the breadboard. So that's where you want to put it. If you put it anywhere else in the circuit, you're going to short all these terminals. So don't do that. Put it across the spine of the breadboard. Okay. Great. Once the threshold pin resets the flip-flop, the gate transistor is turned on, allowing current to flow from pin 7 to discharge to pin 1 or ground. So what happens when threshold then, so your trigger started this thing outputting current here, and then eventually the threshold pin the threshold is greater than 2/3 VCC, at which point it resets this flip-flop to false, which gets inverted to true here. So true or high here for the gate voltage of this transistor is going to allow it to flow current through it. So it will discharge current from pin 7 to pin 1 to ground. So if you go up here, pin 7 is this. So it'll connect 7 up like with a wire essentially to ground. Okay, it'll allow current to flow like that. And so you can use this to discharge something. That's exactly what we're going to do with it, is use to discharge a capacitor. So, all right. So that is the 555 timer. That's how it functions. There's some subtlety to it, and I kind of glossed on the flip-flop. If you want to look up SR flip-flops, you can get into some fun stuff. Yeah, but I'm not going to go into too much detail. I think you guys understand, hopefully, the general operating principles there. So the LED 555 timer circuit is what we're going to build with a 555 timer. So we're going to take that 555 timer and we're going to put it in into a circuit. There was a presidential candidate who had a 555 tax plan a few years ago. People made fun of him because he was like the, I don't know, Godfather's Pizza or Pizza Hut or Domino's like CEO, and they were like making fun of him because it was like such a ridiculous thing to do, and you're running for president to have like a 555 deal, tax deal. In retrospect, that was pretty mild, I guess. Okay. So, the LED 555 timer circuit. We will be building the circuit diagram of figure 6.3. That's this guy. And so there's our 555 timer. Notice right off the bat that all of these pins are all mixed up. So they're not in the order that they appear on the actual chip. So it is what it is. Just make sure you read the number and not the position on there. So we've got a 9-volt battery that's connected to it. It's powering the circuit. We've got 3 resistors, R2, R1, and R3. A capacitor, which we'll start off with a 1 microfarad capacitor, then we'll replace that with a couple other values. And the 555 timer and an LED. The idea is that this circuit is going to turn on the LED and then turn off the LED and then turn it back on, turn it off at an interval that is controlled by C1 and R1. So those are the two, primarily those are the two variables that control the timing here. So, great. Okay, so this circuit charges, then discharges the capacitor C1. The capacitor's voltage is applied to both pins 2 and 6, which control the flip-flop through the comparators, right? But which are compared to different voltages, right? So you might think, wow, it's kind of weird that we're putting the capacitor voltage into 2 and 6. 2 and 6 are the ones that, so that's 2. That's 6. These are the ones that we're comparing to the 1/3 and the 2/3 VCC. So it's at first it's kind of like, well, why did you put the same capacitor voltage into both? And the important thing to recognize is that we're actually going to be comparing that voltage to 2 different values at each comparator here. So the trigger value will get triggered at a lower voltage level, and then the threshold will get triggered at a higher voltage level. So, good. So the capacitor first charges up enough to trigger the output 3, which flows to the LED, through which through R3, which limits current. I think there should be parenthesis there. Once the capacitor charges up to initiate the reset, the LED turns off and the discharge transistor turns on. So let's let's work that out. So what first happens is start to charge up this capacitor, okay? And it's connected to 2 and 6. It reaches a level of 1/3 of VCC, and suddenly